So hello everyone. I really appreciate that you come into my talk enhancing vulnerability detectors with large language models, since there is currently collision with Vitalik's fireside chat, so I really appreciate it. So my name is Jan, and I'm security researcher at Eki Blockchain. We are doing blockchain security audits and also developing some open source tooling where about one of the two we will be speaking today. Also, we are onboarding developers to blockchain at the local university, or we are occasionally doing some online courses. We work in PaaS with clients such as 1inch, Lido, Safe, or XLR. So that's just the interaction about myself and the company, and we need to start with static analysis, then we dive into its interconnection with the AI. So I would just like to ask, please raise your hand who knows something about static analysis. Awesome. And who's actively using that during the development? Yeah, maybe we will get to the reasons why it is in this way. So static analysis is basically about extracting some information from the code. And we can do it in two ways. And first one is detectors, where we are basically searching for some patterns that can lead to vulnerability or some code quality issue. And the second way is just about printing some useful information about the code, such as you want a printer which will print you all only owner modifiers in your code base, and you can see all the invocations and the respective functions of these modifiers. So it can be handy when you are trying to understand some code base and so on. Yeah, so there is example of some detector. If you know Slater or other static analysis tools, or transit detector is usually the first one which is implemented. And this is example of the output where you can see that at some position in the code there can be some possible entrancy, and you see there that subdetections which could be the attack vectors. Then example of a printer is, for example, for a storage layout, where if you are doing contract upgrades, then you can print your storage before and after upgrade, and you can see if there are some clashes in the storage. And this brings us to the tooling. So the static analysis tooling is mostly based on some sort of intermediate representation model that is built on top of the AST, which is produced by the Solidity compiler. So when you want to have some static analysis tooling, you will probably need some IR model. And there are currently two leading frameworks, and that's the Wake and Slater, which build open API over their intermediate representation model. So example, this is just a big picture. We don't need to dive into much, but this is how the IR nodes and the whole tree of the model looks like. So if we will just stay at the top, we have there contract definition in the green square, and after that is function definition. So we can check it on the example, where we have some contract. For example, that contract has two functions, get token storage and write token storage. And we want to write a printer. So if we will be using Wake, we can just simply add this one function, which is a special function called visitor function. And this visitor function is just jumping over all the nodes in the intermediate representation model. And this visit function is jumping over the function definition nodes. So in the body of the function, we have two prints, where we print like the name of the node and then the parent. Here you can see that if we will run the printer over the contract which is above, we will get printed the function names and the contract where they are placed. So this brings us to pitfalls of static analysis, where the biggest problem is that the fully algorithmic approach is not always sufficient because the traditional static analysis does not understand code semantics. So it means that you can have in one code base there can be some valid detection and for one specific detector, and in the other one where it is almost the same, it will not be an issue because let's imagine that in one code base you are working always with one token, and in the second one you can have any token to interact. And so in the first case it won't be a valid detection because the token will be always the same, and for the one case it is safe, but for the multiple cases it won't be. And we can recognize this easily with the traditional static analysis when we are using some heuristic techniques and so on. So if we want to do a safe approach where we will report all the possible detections instead of just don't report it, we will get to high false positives numbers. And that's probably the reason why a lot of developers are not using it, because it will just pollute the output of your terminal and so on, and you don't want just to dive into all the false positives and check it. So we need some sort of human check, and this is where the AI steps in, and we won't do it this way. Like, you can use it generally for some recommendations, what can be, for example, some attack vectors, and just discuss the contract with GPT in general. But we want to be smarter, we want to combine the techniques of the static analysis and the power of these large language models. So the human check can be performed by these language models by combining some specific prompts with algorithms in static analysis. We were testing that on GPT 3.5 and Claude, and basically on some specific cases, GPT-4 was just enough to be very successful. So to explain it better, we have a case study, and it will be about a detector that is called Ketchak 256 different hash, which can be kind of confusing name, but what it is doing is pretty simple. The detector can recognize difference between expected hash and the hash that is used in the code. So there is like a developer convention when you are using some magic numbers in your code base, then you have there code command which explains the magic constant to not confuse any code reviewers, other developers, and so just to not add some issues in the future development. So exactly when you are using, for example, hashes for storage locations, then usually there is a code command which has some sort of string that explains the pre-image of the hash. And the detector is already implemented, so on the screenshot you can see the output of in VS Code where can be seen that there is a mismatch in the last symbol. So how to implement it? So some naive implementation could be like a detect code command near the variable declaration, then extract the expected hash pre-image, and calculate the hash from the pre-image and compare with the hashes in the code. So, but there is an issue that you can use some regexes, heuristic techniques, and so on, but you won't probably catch all the cases. So there can be like a valid solidity code, there can be like some redundant symbols, there can be like wall of text in which there will be hidden some text explaining what's the pre-image, or and so on. So if the human will be reading the code, he will probably find out what was the idea, how was chosen the specific hash. But it's hard to catch all the edge cases without some more personal check. So this is what we are going to address. We want to extract this pre-image from the code command with the language model. So the implementation will be pretty straightforward. We just want to start with some pre-processing part where we will use static analysis to find bytes 32 constants in the code base. There is just a snippet down which does all the logic for that. And it's very similar as we shown at the beginning, how we can iterate through the functions. So we just need to find not the functions, but that bytes 32 declarations. When we have that, we can extract the nearby code command, find the relevant text, and send it to language model. Then we get some output. And that's the thing. We need to somehow parse it. So if you have a constant expression evaluation engine, then you are probably happy. Or you can insert the output to Solidity template, which you can just imagine like a contract where you will get some valid Solidity code and you will place it into the function in the contract, so then you are able to compile it and get the value. And the third option, probably most straightforward, is just to interpret the output as a Python code and use save eval, where the third option is implemented in the snippet on the right. So it's not so complicated. So, but it is possible that some of these approaches fail, that you will get, for example, a long sentence from the GPT or some invalid output. So you want to send the error back, explain it to the language model, so the language model will attempt to fix it, and process is repeated. When the evaluation succeeds, the hash calculated from the code command is compared with the value in the code. So just a high level, the architecture is that we will start with compilation, which will generate intermediate representation model for us. Then we will do the detector pre-processing, so we don't want to send all the source codes to the language model, just some small strings, which are enough. And this will be sent to the language model that will try to extract the pre-image. And then there is the post-processing part where we are trying to evaluate it. If we fail, we will send a fix request, which is another prompt. So they are figuring 2 prompts for the language model. And then it will try to extract the pre-image again. And in the end, we will compare the hashes. So the prompting, like when you start developing with the language models and get more into it, it can be pretty hard just to force a language model to answer with your code. It's still doing things like, I apologize for the confusion, and pollute the output with some sentences and so on. So you need the best way what we found that you can place some special sentence in the end of the prompt, which is basically the last thing that the language modeler read. So he will keep it in mind and can you send the output what you need. And other thing is to get a stable and consistent outputs. So you will send 100 times the same pre-image or the same text, and he will always extract it in the same way. This can be done when you change the attribute called temperature to 0, which is, you can imagine it as emotions of GPT, so the output won't be so emotional and so human. And then there is some also important thing is to cache the responses. So, for example, when you are developing, the detectors are rerun with all the code change, and you don't want to send a request all the time. So, for example, if you will be working in a team, you can have some cache for the team, or it depends on the level of what you need, but caching is important. And I have there the special sentence for you. Like this one is exactly what we are using in the code. And it starts with a take a deep breath. It might sound funny, but these words are really working. Take a deep breath, calm down. Or from the other side, you can say, you are paid for that, do it, or you will be fired. And sentences like that really works. And then we get to some other use cases. For example, unchecked return value detector. It is also one of the detectors that are like polluting the output with a lot of false positives. So developers sometimes don't want to check for the return values intentionally. And this can just help to somehow filter these false positives cases, so make the rate lower. And the second case can be, for example, for underflow overflow detector, which can help you to discover some more complicated scenarios. For example, when you are combining assembly with solidity and you are getting some very complicated statements, which can, for example, go wrong in the places where you wouldn't expect to, then the language model can again help you, this time to bring the bigger true positive rate. So the summary is that in our opinion, language model can help you definitely to make more precise detectors, and also it opens like doors to the world of the detectors that we won't be able to create with the traditional static analysis. So it can be definitely effective for a specific task, rather than running it over the whole code base, as we shown on the one slide, which without any fine-tuning, or at least for now, it won't be usable. But maybe after a few years, we can just run it over the code base, and we don't need a job, and that's it. So if you will be more interested in tooling, then after this, there is a session about VS Code extensions. Otherwise, in the end of the day, we have their fuzzing workshop. And in the Sunday, there is a talk about Wake, which is the tool what we were using for developing of these detectors. And that's it, that's the talk. So thank you. Any questions? Okay. Okay. Just please wait for a mic.
Have you tried to use something except GPT-4? Maybe, I don't know, some custom LLM?
Yeah, we've tried, and we've tried it, I think, like a year ago, and it doesn't have so good outputs like GPT. But maybe if we will try it today, it's rapidly evolving. Maybe it will be better. But
so, yeah, sorry. Did you try to train your own model on your
no.
example data?
Not yet.
Mm-hmm. I get it. Okay, thanks.
Okay, that's it. Thank you.